Hi everyone. All right, we are going to graph the data from Nick's walk that included some stop time because one of the most important things that you would need to know about force and motion and distance time graphing, especially were we to still take an EOG, is what a stop looks like on a horizontal graph. You might be able to predict, and I'm just giving you a hint, from when we saw the flat line graph when like yes on Monday, right? All right, so kind of predict what it might look like when Nick stops based on that flat line, like the hospital monitor or the heart monitor. Beep. Right. I'm not going to say more because I want you to, gasp with shock when you see it. All right, so I have my data table that we made. All right, and then what I'm going to do again is change the data table into coordinates. I'm going to remember that my x coordinate is always my time coordinate, and my y coordinate is my distance in this case, but it can be anything. Like it can be a heartbeat, it can be temperature over time, all different sorts of things can be graphed on a line graph to show change over time. Now remember that the x coordinate is graphed by going to the left, crawl first when you're a baby, and then climb when you get bigger. And the y coordinate is graphed by going up. All right. So when the video started, Nick was at 0 time because no seconds had passed and he hadn't moved at all. So we're going to graph that right here at the corner. And I really already did that for you because that corner shows 0 distance and it shows 0 time. All right. The first one was at 3. The next one was at 3 seconds. That's when Nick was at the 1 meter card on the floor in my kitchen. All right. At 5 seconds, Nick was at the 2 meter card. So the next coordinate is 5, 2. All right. The next one at 7 seconds, Nick was at the 3 meter card. At 7 seconds, he was at the 3 meter card. And then, as you recall, Nick stopped for a while. So at 11 seconds, he was still at the 3 meter card. So the next coordinate will be 11 and show that he's still at the 3 meter card. All right, then we have 12 seconds and he was at the 4 meter card. This looks like he sped up a good bit, which is what he was supposed to do. Then at 13 seconds, he was at the 5 meter card. Then at 14 seconds, he was at the 6 meter card. And then what I think I'm going to do is do this. It still says 14, but we'll go ahead and just assume that Nick didn't go from the 6 to the 7 meter card with no amount of time passing. So even though the timer says still 14, it was probably like 14.5. So I'm going to make the next one 14.5. Like 14 and a half, right? Because 0.5 is 1/2. 14.5, and then he was at the 7 meter card. I probably should have done that on the other graph that had a number like that. All right, and then the last one, at 15 seconds, he was at the 8 meter card. So all that's left to do is to graph this data, which we shall do, and it will be so much fun. All right, we're going to graph 3, 1. And remember, the first number is the crawl number. So we're going to crawl over to the 3, and we're going to go climb up to the 1 and put our point right on the line where they intersect, not in the spaces. All right, next, we're going to crawl over to the 5-second line and climb up to 2 meters. So at 5 seconds, Nick was at the 2 meter card. 7 seconds, he was at the 3 meter card. So we'll go over to 7 and go to the 3 meter card. All right, and then at 11 seconds, we'll crawl all the way over to 11 seconds, and then still he was at the 3 meter card. So this coordinate is 11.3. All right, next we're going over to the 12 meter card, and then going up to, the 12 second. So we went to 12 second, and that's when Nick was at the 4 meter card. All right, at the 13th second, Nick was at the 5 meter card. At the 14th second, Nick was at the 6 meter card. And then to show halfway in between, I'm going to go right here in between because I have that at 14 and a half seconds, that's when he was at the 7 meter card. So it's going to be right there, and I'm going to do the 7 meter card right here. All right, and then last is 15 and 8. 15 and 8. So Nick was trying to be constant, but he accelerated just a little bit. All right, and now if we connect the lines to make our line graph, you see that at the beginning, even though it's not perfect, we were attempting for a slow constant. So I'm going to connect it like that so that you see that we have a diagonal that is not very steep, right? And then when we connect the next 2 points, you still see it? Yeah. You can see that when Nick stayed at the 3 meter card, he didn't move, then the line becomes flat. And that's called a horizontal line. A horizontal line on a distance time graph always means that motion has stopped. And that's an important trend for you to notice. And I was giving you that hint to think back to the heart monitor. If someone dies, their heart stops beating and it just goes beep to show that time keeps passing, but there are no more heartbeats. Well, in this case, time kept passing on my stopwatch, but Nick wasn't going anywhere. His motion had stopped. And then Nick's instructions were to walk really, really, really fast. And I'm going to kind of just pretend he was able to walk at a perfectly constant speed, which you can see in general, he did pretty good. Now, what I want you to notice on this graph is that here we have a stop in motion, which is a horizontal. A horizontal line is always a stop, a flat line. All right, I have a feeling that your art teachers, Miss McGee or Miss Mims, or at some point in your life talked to you about a horizontal when they had you draw the horizon, like where the ocean meets the sky. That flat line is the horizon, and that always helps me keep horizontal straight. The other way, like to make in my head, the other way is that my daddy used to always say when he was taking a nap that he was going to go get horizontal, when he would go lay down. So that always helped me remember the difference between horizontal and vertical. All right. And then over here, we have a slow constant. And we know that it is slow because it's not very steep. The slope of the line is not very steep. And that is a trend that we can spot anytime to see the speed of something. If you see a horizontal that's like a baby roller coaster hill instead of a big steep one, then you know that you're going at a slower speed. The other way to remember that a slow constant is kind of flat is if you first keep in mind that an actual flat line means stop, then if you have a horizontal, a diagonal that's just a little steep, that's close to a stop, right? A little steep is almost a stop. So when you have it kind of flat like that, you know you're going really slow because it's, almost a stop, right? And then you notice that this part of the graph right here got way faster. So I'm going to label that with fast constant. Right? And when you have a fast constant, then the slope is very steep. Very steep slope. And if you know these things, then it makes it really easy to look at a graph and to be able to explain the motion that you see, right? You can always just take a peek at any distance time graph, and when you see a flat line, you see that someone has stopped. And it won't say that on the graph, but you just know because you know a flat line means that the motion has stopped. And if your diagonal isn't very steep, you know they're going the same speed, but just really slow. And then over here, where Nick was going way faster, you can see that it made almost a perfect diagonal, but much steeper. All right, so that's 3 things that you need to know: a slow constant, a stop, and a fast constant. Remember, constants are always diagonals, like if it's a moving constant, right? And then a stop is always horizontal. All right, and now you have a little assignment to make sure that you don't forget about the slow constant, the stop, and the fast constant. All right, y'all. Thanks for watching my video. Love you, man. Love you all.